And the discussion will be done by Yuri Poutanen, who is here, and Saika Vrtilek, who I hope had enough coffee to be awake.
It's very early for him.
I can testify that jet lag does not require jet travel.
Okay, good to see you, Seko.
It's good to see you too.
Okay, so we agreed that we will split this discussion section in the 3 parts. I will give you some short introduction. Hopefully it will be short, less than the length of the discussion. And then there will be Sako will continue with a couple of small slides. And then of course we will have the discussion itself. So the organizers asked us to discuss very broad topic of multi-wavelength spectroscopic or spectrometric and polarimetric observation of quasars. That's absolutely impossible in half an hour. If we're going to go from the radio to GeV band, let's say, or TV, which some of the microquasars observed, that will be impossible. So at least we thought that we will concentrate on somewhat narrower topics, let's say on the optical infrared emission there, and therefore we will not discuss objects like Cygnus X1 and Cygnus X3, where the optical infrared emission is completely dominated by the companion star, but we will go to the low mass X-ray binaries. And I will be provocative here because most of the talks here during the conference were saying that the jets producing everything or almost everything. And I will just show you some example and you will decide yourself whether this is true. For example, in our paper, so some of the discussion leaders also advertise their own papers, so I will do the same. In our paper by Ilya Kosenkov as the first author published last year, MGX39-4, we showed that the emission in the optical infrared band might be actually composed of 3 components. Here, those who are, let me see, those who are in the audience probably see my green pointer. The optical infrared band is there, and you can see that in the hot state, where you see these infrared flares that we discussed also yesterday, one thought that, okay, this emission infrared flares is produced by the jet, and we have opposing view that most of this emission in the infrared flares might be produced on the hot flow, where you have some relativistic electrons, non-thermal electrons producing infrared emission. And in the end, I think in this paper we showed that both views are wrong, and likely both components contribute to the optical infrared emission. Why we say that? Because in the WISE data that was also mentioned today, which are this here about few points there, you see very strong variability on the time scale of some tens of minutes. And at the same time, in the optical part, in the near infrared, you see almost 0 variability, or very little. So it's clear that if you think that there is a jet contributing to the mid-infrared part, and this is actually strongly variable, in one of the observations in this pink here, you can clearly see that the jet contributes almost nothing, okay? So clearly that the jet is very strongly variable. There is a cutoff at somewhere the mid-infrared, and you have an additional component which is, in our view, is the hot flow that is much less variable. Okay, then if you go to the soft state, and here the spectrum is shown with this orange color, we see no thermal emission. So it seems that, okay, we don't see the jets in those states, we don't see the hot flow in those states, because most of the emission is produced by the irradiated accretion disk. And it means that depending on the state, emission might be dominated by 1 or 2 or 3, or you can also have 3 components can contribute to the to your spectrum. Of course, polarization was mentioned today in the first talk of this session, also as the powerful, rather new tool to say something about X-ray binaries and most importantly, what I would like to mention about the geometry, because polarimetry will tell you about the orientation. Before, we knew about the orientation of X-ray binaries only looking at the radio jets, basically, or sometimes on the X-ray jet too. But so basically, you know the position of the jet on the sky. Sometimes you know the inclination because you see superluminal motion. But now you can have access to polarimetric data, which also can give you a clue about the orientation of the object on the sky. And here are just some couple of examples of this now famous microquasar. And yesterday, Piki said that there are 159 papers on this, on the ideas on this source. So we have at least 3 papers now discussing polarimetry from this source, and another 4 papers discussing something else. But so our group contributed a little bit. And what you see here on the right-hand side, there is a plot, this Stokes parameters, Q and U, normalized Stokes parameters, where you see that there is evolution of the source from the hot to the soft and to the hot state again. And you can see that so this is intrinsic polarization. So a subtracted interstellar component, yet that in the hot state, it was like 0.5% only. And in the soft state, it was even low. There is this 0.3 here in the B band, there is like 0.2%. And in the decaying hot state, we see basically no polarization. So first thing to mention, to get from here, it's very hard to do these observations because the accuracy that you need to get the statistically significant variations from one state to another, you have to be very accurate. Yeah, you have to determine very accurately your instrumental polarization. In our case, it's negligible. Here is 10⁻⁴. We can calibrate it even better. You have to be very careful subtracting interstellar contribution. You have to have a number of stars in the field of view, observe them. You have to do it like observe polarization standards, zero polarization, high polarization standards before the observations, in the middle of the observations, after the observations, to do proper calibration. This is very important if you want to get reliable results. What here is interesting that in the hot state, since we talk about geometry, you see that the polarization angle is 25 degrees here. This is in this plot, you have to divide this angle by 2 to get the polarization angle. So it's 25 degrees. It turns out to be parallel to the position angle of the jet that you can see from radio and X-rays. We first thought that, okay, it might be produced by the jet, but actually from the wavelength dependence, it doesn't seem so. But instead, what we found that the high polarization, the rising hot phase, is produced exactly during those phases of the outburst where we have winds. There are papers by Munoz Darius who show that there are winds. There is this red lines there that you see. There are winds are detected, and polarization is high in this windy states. Okay, it seems to us that this is somehow there is a relation between high polarization, 0.5% polarization, and the wind detection. So we claim that probably the winds are responsible. Okay, in the soft state, the position angle is very different, and we don't see the wind. So again, something's changing. So obviously now from polarization, now we again see that there are different components contributing. We don't know exactly what is producing this polarization in these states, but it's really interesting that this is varying from one state to another. Then I would like to say a few words about quiescent state. Most of the talks here were discussing the bright states because that's easy to observe. But now we have quiescent state. The X-ray luminosity is 5 orders or 6 orders below the bright states. So it's very difficult to observe. The optical emission is also very weak. You see the star, you see some emission from the accretion disk. And here is the 10-year-old paper by Froning. We have emission from the famous microquasar A062000. And there is optical UV emissions completely dominated by the thermal emission from the disk. There is a stellar contribution is still very low. What's interesting that there is UV excess and very little discussion in the literature about actually the nature of this UV excess. And I tried to go through the literature, maybe you can help me, and if there are anybody else who is discussing the nature of this UV excess. In the paper that we put on AstroPage last Friday, now we've mentioned a few times, we actually find the similar UV excess in MAXI 1820 plus 070. Now it's F-nu, not a new F-nu, but there is a swift detection of this UV excess. And what's interesting also, we see very high polarization, about 5% in the B band. There are these blue points, very not clear whether there is orbital variations. We cannot make any the signature, but also the polarization is very blue.
Note from the chair. This was already 10 minutes introduction.
Yeah, we will go now. That's the final slide actually. Then Saka will take over. What's interesting that the polarization angle now is very different from the jet position angle, not parallel, but it's 45 degrees. The conclusion was here that there is something probably related to this UV excess producing high polarization, and we can measure the deviation or the separation of we think that's the disk somehow related, the orbit of the spin of the orbit and spin of the jet, or the position of the jet black hole spin are misaligned. So here, questions that probably would like to discuss that there are some sources of emission, slightly many sources of emission that we would like to know. What are they? Some of them are polarized, some are less polarized. We would like to know what is UV excess, what's the region of polarization that I discussed. And there are some, and the question is, what are the observations that actually we need to answer those questions? Because we need simultaneous, maybe from mid-infrared at least to the X-ray observations, broadband polarimetric observations, and even spectral polarimetric observations. Now, I think Sako would like to take over and say a few words.
Well, I'm not sure I should say too many words. We'll have no room for discussion. Yes, as Rob Fender pointed out, I guess Tuesday, the X-ray binary community is very rich in data, and all these sources have been observed multiple times. Here I'm showing two sources that have been particularly well studied. And I have tried to organize my ideas by making a matrix of the components of these systems and how they interact with each other. And at some point I got tired. There are lots of question marks, but in the upper half of the diagonals, I show the actual measurements that can be made. In the lower half are the wavelengths that are necessary. So obviously multi-wavelength studies are necessary. And of course, there are many components that I don't have here. I mean, I'll have to apologize to Joey for not having a disk wind. And it seems we'll have to have different ones of these for different states of the systems. There are many other components I haven't considered. So one of the things that we have really been lacking in is modeling that is holistic. We have lots of models of jets. We have lots of models of disks. We have lots of spectral fitting, lots of timing. It's time to actually try and put some of these together in a way that can be compared directly with the observations. So if you go to the next slide, I won't go into details here. I had more details. And here are a couple of models. The upper one was actually done by a student of mine, Kachura, and it's fairly rudimentary model, doesn't have relativistic things. And it doesn't include a jet, by the way. So another thing is, what I've shown here is the two states of SIG-X1. This seems to have gone sideways here. And in the upper panel is the low hard state, which the outflow from the hemisphere that faces the X-ray source is noticeably slower than the wind coming from the hemisphere that lies in the X-ray shadow. And if you add a jet model to these simulations, they will influence both the wind dynamics and introduce further shocks. So I'm not going to go into the details of this particular model per se, because that's not necessarily the best model, but to point out that you can see that variations, the interactions between all these different types of components varies throughout the binary orbit. So not only do we need to do multi-wavelength observations, because all the different wavelengths cover these components, we also have to do it around a full binary orbit. And that's a lot of information. And in order to put it all together, it's best to use things such as, I think it was it's Bailey, who has done both spectroscopy and timing studies together, so-called astrotomography. Because what you can do is you can take these holistic models, which we'd like to see more of, that includes all the components, and convert them into Doppler space, which Kachura actually did for Cygnus X1. And he used the H alpha line in optical, but if you use, for example, UV lines, you would see many other components. And also the model by Zhu, Stone, and Zhu consider the difference between MRI and spiral shocks. And again, if you take Doppler tomography of, say, SCO-X1, you could actually see these features and decide which one dominates. So what I would suggest is that we need simultaneous multi-wavelength observations around the full binary orbit in order to actually understand the physical implications of the interactions between the components. And we need to put more physics into our models. I think I'll stop there so we have some time for discussion.
Okay, thank you, Sako. I guess we should go to discussion itself, right? So what will be the really interesting topic to discuss? It's obviously that we cannot cover the most or not many of them. Anybody who would like to comment on, for example, any of the future observations that we need to do and how we should do them to at least answer some of the questions? There is a person in the room. There.
Hi, so Vrtilek J speaking. Actually, I don't have an answer, but if I understand correctly, since it seems to be quite complicated in the UV infrared bands, don't we need also to have the radio here? You do not talk about the radio in this. Okay, so for example, in your fit, it seems that if you have the radio, you can I mean, for example, in this fit, the radio helps you a lot to discriminate between the different components. So I think that you have to also to include the UV if you want to understand the optical. You have to include the radio if you want to understand the optical.
For sure.
Yeah,
I mean,
absolutely, yes.
Yes.
Okay.
Of course, the difference is that radio normally is less variable because it's produced further out.
Yeah.
So therefore, you have to account for that they're not produced at the same place where you probably expect a UV or optical
so you have time, yes, you have timing delay and so on.
This is exactly the same model problem people have in laser research, where you have radios produced far away, and then you have the high energy emission produced more locally.
But then millimeters may help a lot more than, I don't know what is the.
I think it's Alex who mentioned the millimeters might really help, millimeter wavelengths.
Yeah, because
And
if one
certainly
believes
even with the radio, you can see differences in the different states.
Exactly.
So that would help with disentangling things.
Actually, my question is it better to include radio instead of X-rays, for example, to help to understand the optical infrared, or is there any preferences between the different wavelengths? I don't know. To discriminate.
Well, I personally prefer all the wavelengths together. It's hard to coordinate, but it has been done. The last time we did a multi-wavelength that included ultraviolet, radio, X-ray, and optical for SIGX1 and SCOX1 used IUV. I think it's time to do it with COS, which actually can handle the data rate. So I think we need all the wavelengths at once.
Yeah, there is some comment on the online, right? Greg Sivakov.
Yeah, I was gonna say, I mean, we actually, at least for V4 SIG, we are seeing time variable polarization information. I'm working on that with one of my students. But I think overall, I think that's a special case. I don't think we have to worry too much about that. And so I'm not quite as concerned about the location differences in terms of a time delay between the radio and the high energy. Now, absolutely, there's a difference in the physics based on the different locations. That's absolutely critical. Potentially different physics, I should say. But the other thing is, when we think about the UV, there are other instruments besides HST. I mean, there's been a lot of work with UVOT, etc., and that's much easier. It may not be as sufficient. I completely agree, but that's a lot easier to get coordination with than Hubble is. We've tried really hard.
UVOT is excellent, and we're actually currently have a paper led by John Dickey that has been using UVOT on about 30 sources, along with radio, X-ray, etc. No, but the HST is for specifically studying UV lines, which give us a lot of information. And that's something you cannot get from photometry. And especially UV lines around a full binary orbit really gives you where all the different components come from.
Yeah, but the good point here
the COS is not just for photometry, which UVOT is wonderful for, yeah.
Because the trouble is that in UVOT there are quite broad filters with some red leaks, so it's not easy probably to get exact calibration, but at least it's useful. At least if there is access, probably you will see it. Yes. So Swift UVOT is really, at least it was helpful for us, and I think it will be helpful to do monitoring of these sources together with the low energies. Yeah. There is some comment in the room.
Yeah. And for those online, please raise your hands. Online, Poshak will be next, but first hear a comment from the room.
Hi, Marianne Heider here. So I just want to make a really quick comment about the UV, that the Caltech group, Fiona Harrison and Sri Kulkarni, are working on a UV mid-X mission that will actually have some spectroscopy capabilities as well. That won't be too much worse than HST STIS in low resolution. And so we are looking at X-ray binary outbursts with that thing, if it flies, of course. So that will, I think, be really cool in the future.
Maybe not only outbursts, but also quiescent state. Will it be sensitive enough? Or?
Maybe, but it's, yeah, it'll be better for the outbursts, I think.
Poshak Gandhi has raised his hand.
Poshak, go ahead.
So I just wanted to say to Yuri, your results are amazing. The ones for the quiescence polarimetry, that's quite remarkable. Not sure I agree fully with the interpretation, but I think the data are really nice. And I wanted to ask you, have you done this for other sources in quiescence yet? And the second question was also, you said that you weren't certain whether there was any orbital phase dependence. Can you comment a bit about that? Because your error bars do suggest that there is some dependence. I'd really like to hear more. Thanks.
Okay, so the trouble is that we tried some sources, and actually we have the data for another few sources where we see nothing in the quiescent state. Basically, for example, we looked at 466, 64, 46, 41 Sagittarius. We don't see any polarization significant in excess of interstellar. So we will try some other sources. So it's clearly this polarization that we detect in the quiescent state, it's not applicable to all the objects in all quiescent state. Actually, we don't know why it is in MAXI 1820 is so polarized. So that's the answer that we are trying to do it. And we tried to get some time on VLT on Force 2, but we were not successful enough. So probably if you're in the time allocation committee, you can give us OPC, you can give us on some time next time. But the trouble is we are trying to do it. So we have no more results. Here on this graph that I showed, we see variations, but it seems that they're stochastics. We don't see clearly orbital dependence. So therefore, we actually, we are in the, so it's very difficult to understand what is this. In the B band, polarization is high. It's clearly variable, but whether it's related to specific orbital phase, it's impossible to say.
Okay,
there's also on ultraviolet, there's a comment in the Slack by Rob Fender, who points out that there will also be the Ultrasat mission. This is Israeli mission with I think German contributions that essentially is built for gamma ray bursts, but will also be able to do other transient science. Anybody knows about Astrosat? Because I remember in Astrosat also there should be some UV capabilities. So
Astrosat is an absolute pain for scheduling, especially for UVIT. And so it's very difficult. There's large parts of the sky you can't look at. I would not rely on it for that. Okay. Unfortunately.
That's a pity.
Other comments?
So, yeah, I hadn't actually finished my general comment, which was that, you know, HST is really hard, but something that Phil said in the Slack conversation was we do have this opportunity with the polarimetry, X-ray polarimetry experiments coming out to really provide an absolute excellent science case for why we need these very difficult to schedule, very rapid turnaround things for the big observatories. So that might be a good key result from this conference, is us moving forward with that idea.
Okay, Jorn, who was there?
So it's Jerome and Poshak who've raised their hands, and I've forgotten who was first. So
Poshak just had a comment, so Jerome can.
Yeah,
Jerome
is the boss. So.
Hi, I don't know if it's related to this question I'm seeing on the screen now, but I just want to make a general comment. This is something that has already been said somehow. The first day, I think, is that we hear a lot about radio, soft X-rays, and so on and so forth, but some of the questions we are raising this week could be answered by looking at the other side of the electromagnetic spectrum towards the high energies. And concerning the polarization, of course, Integral has not been built for that, but we have started to use EBIS, and the SPEED team as well are starting to use SPEED to try and measure the polarization. So of course, we need a lot of photons, and this is done for bright sources. So far, there are only a handful of them that have been detected. It's above 200 keV up to 1 MeV. But this provides also a lot of diagnostics to try and see what is the origin of this polarization. I know that for 10, 15 years, people have been speaking and making simulation about the expected polarization from accretion disk, what we would see in the soft X-rays, how to disentangle the different components. IXP should be launched sometime. There will be a talk this afternoon. So I guess my comment here is really try not to avoid looking at high energies, guys. Of course, the flux are much lower. The number of sources we see are much lower, but it's also a gold mine, I think, to try and put constraints on the different models and obtain new diagnostics.
Yeah, that's a great comment, that at least we shouldn't forget about X-rays and gamma rays. And when the XP will be launched, we will have polarimetric capabilities, and I hope we will have observations of, for example, the X-ray binaries in the optical, in the infrared, and in the X-ray at the same time. So we can actually polarimetric observations. So we can make, we can understand whether the geometry of this emission region is actually different in different bands where they're produced. I think it will be a very interesting experiment to do simultaneous observation in different bands in polarimetric mode.
Poshak?
Yeah, just wanted to say that I agree with Greg that astrosat is a bit of a pain, but if you're interested in quiescence, then you don't have so many timing constraints, at least. So I would certainly follow up and chat with that team. They may be open to observations. UVIT also has other issues at the moment. I believe one of the telescopes is dead or dying, unfortunately, but do chat to them. Yeah.
Okay. Any other comments? The chair says that we have a couple of minutes, so we have maybe time for a couple of comments, suggestions. What else should we do together? Anjay, want to have some?
Well, I should like some theoreticians to sort of step in and do some more holistic modeling. I mean, I think it's wonderful to model the jet by itself and the disk by itself, but how about the interactions of all these things with each other? That's very important. But it's too complicated, maybe.
Okay, Anjay wanted to say something. Anjay, go ahead.
Well, I actually have a question to radio observers. Signal-H1 is a persistent source, and it's been observed in radio for many years, a lot of times. Also, there was this relatively recent campaign, Chalkbox, and there is basically not a single polarimetric observation of Signal-H1 in radio. I wonder why. Is it difficult, or?
Chiara, do you want to answer that?
No, actually, I wanted to just point out that the model that we presented was trying to do exactly that. So trying to model the multi-wavelength emission, because we think that that's the key to constrain the parameters of the whole system. So that's our main selling point, I would say.
I'm sorry, so I must have missed your presentation. I only start watching at 5 a.m. my times. But
yeah, I'm sorry.
Which day was it? And I will look at
today,
it.
Was this session.
Okay, thank you.
You will be able to look at the YouTube.
Yes, yeah, exactly.
All of the presentations.
I look forward to that. That will be good.
Okay, thanks.
Our chair says that its time was over. And I thank all of you who participated in this discussion. I hope that there was something useful that came out of that. So certainly we need to do more observations and phase resolved, orbital phase resolved, and the different wave bands, that's for sure. And even famous object like Cygnus X1, it seems that we don't have enough data. So which is amazing still. And good luck to all of us, and let's hope to have better data and better models. Thank you.
Yeah. Thank you.
Yeah. I'm only sad that I have Italian time, but not Italian food. Bye.
So we'll all reconvene in 3.5 hours in whatever time zone that you're located in. And I think Elise wants to say something.